the prime location of any security critical variables parameters. So we talked about this, alluded to this before. In 2003, there was an attempt to insert a backdoor into the Linux kernel. And this didn't actually make it to a shipping kernel. It was detected before that, thankfully. But here's the code that accomplished this particular backdoor. It was in the syswait4 function in exit.c in the kernel. And wait4 just tells a process to basically wait for its child processes to terminate before proceeding. So here was the piece of code that was inserted, and it checked the options, and it said if the options that were passed into this function have these two flags set, and the current UID was 0, meaning it was running as root, then return this particular return code. Well, if you look a little bit more closely, what actually is going on here is that it wasn't doing a comparison to see if the UID was 0. It was actually assigning the UID to 0. So you've got an assignment instead of compare, which, if you're not watching closely, it's a common programming mistake. Unlikely common programming mistake to happen in this piece of critical code, which is why it kind of, I think the person who wrote it tried to sneak it under the radar. You could tell that it was somebody that was fairly familiar with how the Linux kernel works, because basically you would never pass that that combination of flags, wclone and wall. They're redundant. They're overlapping basically. Wall includes wclone. So you would have to. There's no chance that somebody would accidentally call the wait function in this way. So it was very, very sophisticated. Actually, one other thing to mention about this one is that probably the only reason it was detected was the mechanism by which the person tried to insert it. They actually directly manipulated the files in the CVS tree. They didn't actually make a valid commit to the tree. They actually went to where the CVS root was and modified those files, and then I guess whoever came in after them, tried to check something in or do an update or some other actual CVS operation, got some sort of weird error or some indication that files were out of sync or something like that. If it had just been a normal check-in, I don't know, there could still be a backdoor in the kernel today, because somebody might not have actually seen that anomaly in the CVS. Here's another one in the X server, and this one, I'll start by saying that this probably was an implementation error, because again, it's another one of those common types of mistakes. But there's really no way to be certain that it was implementation error. But this is a pattern that a manipulation of security critical parameter could take. In this case, with the X server, there are some server options that were designed to be restricted to root. So only root could say, set my module load path to this particular location, or use this configure option, which presumably does something useful. If you look at these two sections, focus on the top section, where we're setting the module path where we can, where the X server is going to load modules from. And you can see in the first conditional, it's going to say that if the user ID is 0 or root, or get EUID, which is get the effective user ID, what the process is running as, is not root, then go ahead through and allow them to process this module path option. The bug here is in the conditional itself. If you see the first part of the conditional calls the get UID function and compares it to 0, whereas the second part of the conditional compares the get EUID function pointer to 0. There's no parentheses, so it's not actually calling the function. So unless basically get EUID's memory address, where it's located, that function is located in memory, is always going to be non-zero, and that part of the conditional is always going to evaluate to true. So the arbitrary loading of modules is going to that conditional just basically becomes ineffective. the bottom one suffers from the same symptom. They're doing they're not calling the function, they're just comparing the function pointer to 0, and it's never going to be 0. So detection, this can be very application specific. Other than operating system code where you kind of, you know that there are going to be certain things that are security critical, like the UIDs that we talked about before in the Linux kernel. In an application, you kind of have to have a little bit of design information to understand, what are those variables called that are that store the current user ID or the current logged in user or any other anything that's critical to that particular application. But the mechanisms by which those are altered or manipulated are kind of the same. You can still look for assigns instead of compares in any piece of code. You can also look for a conditional where there's an assignment. The right-hand side is not the return value of a function. It's pretty common in C to allow in a conditional to actually put a function call in there, and then if the function call succeeds, then that evaluates to true. But if you find cases where the right-hand side of that conditional is not actually a function, or it's a function that always returns the same value, that could be that's obviously code that's not going to be doing what it looks like. Logic expressions in any security critical code that that are kind of botched, like a short-circuited expression. There's an example there. If true or is authenticated. Now somebody's not going to put true, but they might put something that always evaluates to true, kind of like the function pointer comparison. So any sort of logic expression that gets short-circuited it could be potentially suspicious. Here's some things that kind of didn't fall into those other categories, but some other things to look for. They could span really any of the categories. Embedded shell commands is just something that you always want to look for because it's very easy to just search for particular strings. Time bombs, things that set up particular time windows of opportunity to allow certain functionality to be switched on or off selectively. Rootkit-like behavior, kind of alluded to that before with the hiding of the network functionality. And then some other code or data anomalies that I'll talk about. So low-hanging fruit, grepping through source, running for strings and binaries, looking for bin sh, bin bash, bin cache, all the standard ways to just execute a command. Sounds silly, but easy enough to do, and for the time it takes you, you can find something useful through that grep. Obfuscation of static strings, people trying to hide their tracks a little bit, but not understanding that things like base64 and UU encode and ROT13 and XOR are trivially reversible. Any sort of file system usage that looks abnormal, putting a lot of temp files, using alternate data streams in Windows. It's just, who uses that? But it's it's still there. So if anybody's doing that, that could be that's a common way to hide stuff. Date and time library calls, again going back to the API, looking for those date and time calls that might be used to determine during runtime if it's a certain date, or if it's maybe you've got that hidden parameter in the web application, but it only activates if it's the first Wednesday of the month between 12 and 1 a.m. So it's got to figure out that stuff somehow. So you can look for those standard calls to time functions. False positives in detecting these are going to fall into the logging category. A lot of programs, when they create log files, need to get the time to put in the file. Execution time calculations that people leave in there for just for QA purposes are going to do some calculations on the current time, before and after an operation, for example. Protocol timestamps, if it's implementing custom protocol and it's got to put the current time in a field or something, you're going to see those calls. So there's potential for a lot of false positives here. Rootkit-like behavior, I won't go over these in a lot of detail, but basically looking for some of these things that are indicative of process hiding or Win32 hooks, DLL injection, injecting code into another process, keystroke logging. And again, these are often implemented through very specific Windows calls. On the Unix side, in Linux, there's some ways that you can write in code to do hooks and net filter, custom protocol handlers that might be in there to look for, say, a magic packet or something like that. So this is another whole research area. Rootkit.com's got a lot of good techniques for this stuff. I would say that the false positives here are probably going to fall into the category of if the application that you're looking at is, let's say, a debugger, well, then it's going to have to attach to processes and query the memory pages and do some of these things. But I don't think that there are a lot of programs that legitimately would need to call these functions. So so the presence of some of these can be an indicator that something is trying to be hidden. And finally, the code and data anomalies. Any self-modifying code, the PHP examples that do the eval and rewrite themselves, or the OpenSSH example where you had the block of ECB that XORed itself and then dumped out to a file. Anytime the program manually writes into a code page or jumps into a data page, I mean, that's not normal. And that falls into the self-modifying code category. Also, unreachable code. If I, as a developer, check something into a repository, and let's say I just check in a function and nobody calls it, well, technically it's not a threat at that particular point. But what somebody could be trying to do is kind of a multi-stage insertion. So first they check in something that does something malicious, but never gets called from anywhere. So it could be masquerading as a kind of a piece of debugging functionality. So the person reviewing the check-in says, "Oh, that's just for debugging. It's not, nobody's calling it. It's just in there. Somebody will turn it on later if they need it, that sort of thing." But when what somebody could do next is in a completely separate check-in. Maybe they wait 6 months later. Maybe they wait a year, and then they just insert something else that calls the debug function. Somebody else is reviewing that check-in, or maybe it's the same person, but they don't remember it. But the fact that you're reviewing these little pieces at a time may allow the person inserting the backdoor to get past some of these code auditing mechanisms. So watch out for unreachable code. Okay. Backdoors and malware. Kind of an interesting idea, I suppose. Any application can really contain a backdoor, even things that are advertised themselves to be backdoors. So you may install, the Sub 7 or this Optics Pro backdoor on your system, and you configure it with a password so that you can access it remotely. Some people use these, back when they came out, just as remote control mechanisms for kind of utility. So it's kind of like an alternative to a remote desktop or something. You just install this, and now you go somewhere else, and you can connect back to your computer, and you've set it with a particular password so that only you can get in. Well, it turned out that in both of these cases, with these very popular backdoor packages, that the authors had embedded master passwords. So they made sure that they could always get in to these things, once people had installed them. In the first case, the Optics Pro case, once it was kind of detected and somebody